So we are going to evaluate the limit as n approaches infinity of n to the b minus a times 1 to the a plus 2 to the a all the way up to n to the a divided by 1 to the b plus 2 to the b all the way up to n to the b, where a and b are both greater than -1. Now the first thing I see when I look at this limit is this 1, 2, 3 up to n on the top and on the bottom, and that reminds me a lot of Riemann sums. Now, Riemann sum is a sum of the form I from 1 to n of some function of I over n times 1 over n. So this means we get 1 over n, 2 over n, 3 over n, all the way up to n over n. And then that is going to get multiplied by 1 over n. We add those up. Now, in this case, we don't have I over n. We just have I. So this is 1, 2, 3 up to n. But we want 1 over n, 2 over n, 3 over n, and so on. So we really want to divide all of these by n to the a. Can we do that? Well, in fact, we can, because notice over here we have n to the b minus a. This thing right here is the same as n to the b divided by n to the a. So in fact, we already have this n to the a that we need to transform this into a Riemann sum. So let's rewrite our limit right here as n approaches infinity. First, we'll just look at the parts with a in them. If we divide all of these things by n to the a here, we're going to get 1 over n to the a plus 2 over n to the a, and then so on up to n over n to the a. And then we have times something over here with b's. Let's not focus on that right now. Let's focus on this. We want to turn this into a Riemann sum. So we have f of I over n, and we have adding up from 1 to n. But we're missing this factor over here. We want to have a 1 divided by n. So what I'm going to do is just take this, multiply by 1 over n, and then I'm going to multiply by n again to cancel it out. And we'll see if we can evaluate this limit using this as our first Riemann sum and then looking at the rest of the limit. Now, this time we have 1, 2, 3 up to n, but it's in the denominator. But remember, if we take the limit of something divided by something else, that's the same as taking the limit of the top and then dividing by the limit of the bottom. So in fact, we can split this up into two limits right here. If we divide by the limit as n approaches infinity of, we have 1 to the b plus 2 to the b plus up to n to the b. Can we do a similar process on these b's as we did on the a's? I think so, because notice that we have this n to the b that we were missing. But remember that n to the b in the numerator is the same as dividing by n to the b in the denominator. So we can actually write this as 1 over n to the b plus 2 over n to the b, and then plus n over n to the b. And now we've accounted for everything in this limit right here. So this almost looks like a Riemann sum again. We have 1, 2, 3 up to n. Each of those is divided by n. We're missing this factor here again, this 1 over n. Is there a way that we can get that? Well, in fact, there is, because notice on the top of our limit here, we have this multiplied by n. And we weren't really sure what we were going to do with that. But in fact, if we think about this n as being 1 over n, we can actually bring it to the bottom. And then we have this whole expression here times 1 over n. So now we actually have a Riemann sum divided by another Riemann sum, and they're both going to infinity. Remember that if we do the limit as n approaches infinity of this sum right here, this Riemann sum, it's going to turn into an integral, the integral from 0 to 1 of f of x dx. So now we can actually plug that in to these two limits right here. This is going to be equal to, well, on the top, we're going to get the integral from 0 to 1. What is our function? Well, our function is whatever we're plugging in I over n. In this case, it's actually going to be the input to the power of a, because we have 1 over n to the a, 2 over n to the a, up to n over n to the a. On the denominator, we will again have an integral from 0 to 1. This is in the exact same form as the top. We just have to have x to the b this time, dx. And this is fairly easy to evaluate using the power rule. Remember that both of the powers are greater than -1, so we don't have to worry about natural logs, which means we're going to get x to the a plus 1 over a plus 1, evaluated at 1 and 0, and then divided by x to the b plus 1 over b plus 1, evaluated at 1 and 0. Now if we evaluate these at 0, we'll just get 0 to some power. That'll cancel out. And then 1 to some power will also cancel. We'll just get 1. So in fact, what we're going to get is divided by a plus 1 right here, and then dividing by 1 over b plus 1 is the same as multiplying by b plus 1 right here. So in fact, the way that we solved this problem was we looked at the original limit, saw this 1, 2, 3 up to n being added together, and thought that looks a lot like a Riemann sum. We can use this n to the b minus a to split it up into two different limits where one is actually in the denominator, so we can take this thing in the bottom and also transform that into a Riemann sum. We get two integrals and evaluate them just like this.